In this video, we continue our discussion of infinite series. In particular, we look at the direct comparison test. The direct comparison test is sometimes called simply the comparison test. It consists of two parts. In both of the parts, we have our given series, a sub n, which we are going to be comparing to a new series, b sub n. Now, there are two key elements to that comparison. First of all, there's an order, meaning which series is going to be larger than the other series. And secondly, then, based on a specific order, there's a conclusion that's upheld. And those two things together will combine to give us the statement of whether a sub n converges or diverges. In this video, we are going to particularly look at case number 1 right here. So let's get to it. The direct comparison test, part 1, states that suppose there exists a finite integer capital N such that the terms in the series a sub n and b sub n are arranged such that 0 is less than or equal to a sub n is less than or equal to b sub n for all values greater than or equal to this finite n. If this arrangement occurs, then if the series b sub n converges, it implies that a sub n converges. Wow. This is the first time we're using a test which takes our original series, a sub n, and compares it to an entirely new series, b sub n. What does that mean? I'm an extremely visual person, and so I like to take text and convert it into pictures. So I want to do that now. First, I'm going to start with my given series, a sub n. And I observe that a sub n is less than or equal to b sub n, which means the terms in the series a sub n are actually smaller than the terms in the series b sub n. So those terms would be larger. And pictorially, I picture this as two disks, a smaller disk inside a larger disk. So let me draw a sub n as a smaller disk sitting inside b sub n, which is a larger disk. Now, what does this test tell us? It tells us that as b sub n converges, what does that mean in terms of my disk? Converge means kind of converge to a point, shrink, go smaller and smaller. So I'm picturing b sub n converging or shrinking, getting smaller and smaller and smaller and converging to a point. And as b sub n converges, right, it gets smaller and smaller and smaller. And what's happening as it's converging? It's forcing a sub n to go with it. So as b sub n converges, then a sub n, because it's smaller, and inside it must also converge. That's the way I like to think of the direct comparison test. Now, what does that look like mathematically? Well, let's do two examples. Example 1. Use the direct comparison test to show that the following series converges. We have the infinite series n equals 1 to infinity of 1 over 2 plus 5 to the n. Now, as I mentioned in the comparison test, we have a series a sub n and a series b sub n. Series a sub n is our original series, n equals 1 to infinity, of 1 over 2 plus 5 to the n. This is the series which we denote a sub n. We want to compare a sub n to a new series, b sub n. This is where you have to put your thinking cap on. we are going to pick a series similar to a sub n, but a series with which we know how to determine the convergence or divergence, like a simpler part of a sub n. I'm going to choose b sub n to be this part right here, 1 over 5 to the n. And why would I select that particular series? I'm going to choose that particular series because that particular series is, what do we call this type of series? When the variable is up here in the exponent. It's called a geometric series. This is a geometric series. And I know what geometric series do as far as convergence goes. Geometric series will converge if the absolute value of r is less than 1, and will diverge if the absolute value of r is greater than or equal to 1. What does this particular geometric series do? Recall, we like to list out terms, or at least I like to list out terms, so when n is 1, my first term is 1/5. When n is 2, my second term is 1 over 25. When n is 3, my third term is 1 over 125, etc. And so this particular geometric series, if you recall from our geometric series discussion, has an a value of 1/5 and an r value equal to 1/5. That's the value that I need to multiply each term by to get this next term in sequence. Based on this conclusion, r equals 1/5 puts me in the category where the absolute value of r is less than 1, because 1/5 is less than 1. That tells me that this particular geometric series that I have chosen, b sub n, is a convergent geometric series. Whew! So this geometric series converges. Now, how does that help us? Well, I've done my thinking. I have a series that I want to compare to. I've discovered that it converges. Now, how does it relate to a sub n? We need to compare the order of a sub n to b sub n. So let's write down our nth term in the series a sub n, and that's 1 over 2 plus 5 to the n. The question is, how does that compare to the series 1 over 5 to the n? Which term is larger? Well, that requires just a little more thinking on my part, so I'm going to put a little thought bubble over here. Let me think about this. What do I know? Well, I know for a fact that if 5 to the n is a positive number, which it is because n ranges sequentially from 1 to infinity, then 5 to the n is always going to be smaller than 2 plus 5 to the n. That's a fact. What about 1 over 5 to the n? How does that compare to 1 over 2 plus 5 to the n? I'm going to do one more little thinking bubble here, right? Let's think about this. What are we really saying here? Suppose we have two numbers such that one is less than another number. Let's just throw out here. Let's just suppose that n is 1. So when n is 1, I have 5 is less than 2 plus 5, which is 7. I know that's a fact. 5 is less than 7. What happens to 1/5 as compared to 1/7? 1/7 is actually smaller than 1/5, isn't it? 1/5 is a larger value, a larger fractional value than 1/7. So what happens is when I invert integer values, the sign actually changes, the inequality symbol changes. That means 1 over 5 to the n is actually a greater term than 1 over 2 plus 5 to the n. Or in other words, to translate that into our A sub n and B sub n, we have that our B sub n values, 1 over 5 to the n, are greater than our A sub n values. And this was the order that we were looking for. We want A sub n to be smaller than B sub n, so that as B sub n converges, A sub n also converges as a direct result. Beautiful. So let's write this out in a statement more formally. So we let B sub n be our geometric series n equals 1 to infinity of 1 over 5 to the n. We know that our terms are arranged such that 0 is less than or equal to 1 over 2 plus 5 to the n, which is less than or equal to 1 over 5 to the n. Then, since the geometric series 1 over 5 to the n converges, we have, as a direct result of the direct comparison test, that our original series 1 over 2 plus 5 to the n equals 1 to infinity, also converges. Recall, there are two things you have to make sure you have when you do your direct comparison test. You have to make sure that you have a correct order, and you have to have a statement about what the comparing series does. In the next video, we're going to take a look at another example using the direct comparison test to this part 1 or case number 1 of it.